So in this demo, we will be going over how to create a signal, which will then we will then add noise to that signal, and then create a curve fit from the original signal and the its additional noise to that initial signal, right? So the first thing we want to do is generate the signal, which of course we're going to want its frequency, and then we don't want it to be with any cracks within that signal, like any sharp edges. We want it to be smooth, so we add a relatively high sampling rate that will give us our smooth signal that we would expect from a sine wave. And then of course its duration. And so here we just create the time value, right? So it just spits out time with its respective signal value. And this signal value is just relying on the sine value that uh, we would uh, we would be representing this signal as 2 pi ft, right? Which where this generate signal function will just return t in its respective signal value that we will be using to generate into the plot, right? And then here we're gonna add noise. So we create this function, add noise, where if we wanted to create an offset, I just want to create a very little offset to demonstrate that it's relatively close to the initial signal. So I'm going to do zero point 0.1 uh, offset, right? And um, to do this, to create this noise, we would be doing the noise level times that of the uh, um, uh, generation of a signal value, right? And so then with this value here, we would just be creating this general offset by adding the its signal plus that little bit of noise, right? So that's how we would be getting that vertical offset for our added noise. And so here we're gonna create a CSV value for our signal, all right? Which is done here, all right? And then here we're gonna create a sine function value just so that we can implement it into our thick curve, and and we're just including all things that are to be observed from the uh, initial signal to that of the curve signal, so we can just compare it. And there are several things that we want to compare, right? We want to compare the amplitude, of course, the frequency too, which the frequency should be relatively the same, right? Uh, Major things that we should notice is mainly the offset, but there will be some um, phase change, which is kind of to be expected too slightly. Um, but anyways, then it will return a value that would um, that would be the result of all these factors for the sine function. So then here we would have our fit curve function, and here to create parameters for our initial um, a signal generation, right? Uh, well, our initial signal generation guess, rather, it'll be 1500, right, with its respective amplitude, frequency, phase, and offset. And we would then uh, create a curve fit based off of the based off based off of these initial guesses, right? And from these guesses, we would add along the noisy signal parameters and its respective t. and of course our initial signal value, which we would all be using um, to create an actual uh, uh, array of the output and the input, uh, um, so that we can observe what sort of changes are made to this new signal, right? Because this new signal, this curve fit signal, is depending on the initial signal and the noisy signal, right? So we want to observe how that new signal will be represented now, right? Um, which is of course what the fit curve function is doing, right? Which is returning the output of that new curve fit signal there. And then here we're gonna just generate two arrays, uh, input and output for our clean signal, our initial signal. And then we're gonna then uh, be having a value that's representing the output, the returning value from this add noise signal, which again is we would declare it as the inside parameter as clean signal here, because we do want to we want to know our initial signal um, before we do add any noise, right? Which is clear, of course. And of course, we don't really need to add the second parameter because it's already declared here, of course, right? So that's fine, of course. And then here we're saving into a CSV the noisy signal, right, which will then be used to observe, right? Um, and then here we're gonna tag along as well the output from our fit curve, right? Which is of course going to be using the t that we are the same t's that we're going to be using to observe the um, our initial signal and then our curve fit signal and our noisy signal, right? So it's just they're all gonna have the same t's, of course. But of course, this fit curve is going to be observed with our noisy signal here. Um, right, and yeah, now that we have pretty much everything, all of our output values, now we would just be creating our figure, right, that we want to output and observe, right? So here, we're gonna of course have our different plots. So this plot is going to be a plot to represent our noisy signal, and we already have our noisy signal. We already declared it up here, which is using the add noise function, right? Because this function is returning a value to represent that signal with its slight offset, right? So that would be this scatter one here. And then we would then include a original signal to be observed, which is going to be using the output of a clean signal from our generate signal function. So of course now that we already created that initial signal here, our clean signal, we know that that's going to be a perfect one, right? So we already have our clean and our noisy signal. All right, but now we want our fitted curve that's going to be dependent on those two variables, right? Um, yeah, the output that depends on both clean signal and noisy signal, right? And so that's going to, of course, be depending on this params variable here. So we're going to have params. So we're going to call on it. And then of course, we want to know what each of these things are. So we're just going to make it a little bit more fancy and add amplitude, time, and all this other crap. And of course, we want to show it onto the screen. So further ado, let's see what we get. We would see here that our dashed blue line gives us a pretty good sine wave, right? And then of course we would also notice our offset from our noise, so that is excellent. Um, and then we would see that there are slight creaks to our fitted curve signal because it is trying to make slight adjustments to these little gaps of noises here. So we can see the little flaws of our fitted curve, but it is doing a great job in trying to represent these two signals and create it into one. So generally, I would say that this one was a success in representing a fitted curve um, from both the initial signal and the noisy signal.